Okay, welcome back everyone. So today's topic is topic number three, which is bridge loading, where we will get into depth on what type of loading that experienced by bridges in service and in extreme event, as we're gonna explain in more details. So we successfully finished, again the pen here, the introduction and bridge system and geometry. Today we will focus on bridge loading, which take us 4 sessions in class. The first 3 sessions will be taught by myself. The fourth session will be taught by our industry partner, Mike Kono, who will get us through the history of development of loading per AASHTO through the years. And this will be held on February 13. So please pay attention to his presentation. He has very nice uh, material that will be uniquely presented to the class. So for bridge loading, we need to focus on bridge design objectives. Our objective when we design any bridge. First of all, we need to ensure constructability, which means that the bridge can be constructed easily with local resources, and we are not building or constructing out of a blue structure. Also, we need to make sure that safety or ensure safety by uh, gauging or scaffolding the loads from the bridge down to the foundation, so safely carry gravity loading such as dead load and live loads. Also, um, ensuring environmental loading such as wind, temperature, and earthquake will not damage our bridges or damage to certain acceptable limits. And also special loading like truck braking force or collision, etc. So this is related to safety on bridge side and travel in public too. After we ensure the loading and safety of structure, we need to ensure serviceability, which means that a day-by-day service of a bridge is maintained. So for example, durability should be maintained, that the structure should be durable throughout the service life with acceptable performance related to interaction with environments. Also can be inspectable, so it's easy to go and inspect. Also can be maintainable, where it can be maintained if there's limited damage and upgrade needed. Also, readability would mean that the riding surface is smooth and easy for traveling public. So you don't have a crazy curves, crazy vertical curve or horizontal curves. Our objectives is to ensure hydrology and hydraulics because bridges oftentimes pass through water channels. We also need to, our objective is to build an economical bridge. So number of bridges in the US is more than the 600,000 bridge. We cannot build iconic bridge for every single bridge. So we have to do economical design and also ensure the appearance and ethics. For our course, we will follow the design specification, which is AASHTO LRFD Bridge Design Specification. For abbreviation, we will call it moving forward Bridge Specs. It's a national specs developed by several AASHTO committees. The version that you will be using is AASHTO LRFD Bridge Design Specification 9th edition, which is 2022. The next one will be published, I think, this year. It's published every 3 years, the different editions. It's by American Association of State Highway and Transportation Official, which is the abbreviation of AASHTO, American Association of State Highway Transportation Official. And to access it with your Rowan account, please use this link to download every single chapter from the Ashto. We will be using it throughout the class. And the Ashto, a lot of these packs are divided into 14 sections, from introduction to the general design and location feature, loading and load factors, structure analysis and evaluation, concrete structure, steel structure, aluminum structures, wood structures, deck and deck systems, foundation, abutment, pier and walls, buried structure and tunnels, railing system, and joint and bearing. In this class, our major section that we will be covering are from 3 to 6. For example, today we will cover loading and load factors. In class, it will be distributed over 4 sessions. In this video, I'll make my portion with 3 sessions in one full video. We will have 5 sessions in structure analysis, 4 in concrete and steel. In the concrete, we will include the bridge deck design. We will touch base on bearing design and railing principles. We also will consider bridge design specification from state. Since we are in New Jersey, the most updated specification from New Jersey Department of Transportation, which is called Design Manual for Bridges and Structures, BSDM. The link is here. It's open source, and the edition is a 6th edition, 2016. During the class, as you know, we will have the teams working on a project, 10 teams, and they are assigned a certain state to design different options of bridge systems. In your state, you will require to review your bridge design manual and compare it to the AASHTO. So the class will not cover bridge specification or manuals from the state, but part of your bridge design is to have a literature search to see what kind of addition from those bridge manual or changes if you compare it to AASHTO. Remember, AASHTO is a minimum requirement. So if you go back here to the AASHTO philosophy in LRFD, usually LRFD is design philosophy. For bridges shall be designed to pre-described limit state, which we will explain later, to achieve objective of bridge design from constructability, safety, serviceability, with due regard to inspectability and economy. In general, you have your structure element having resistance bigger than the demands due to the loading on the bridge. If you rearrange this equation, it means that your resistance minus demand has to go more than 0. The resistance or the demand minus resistance lower than 0. In this equation, we are showing demand minus resistance. The demand is related to internal forces obtained from different loading. So they have summation of the loading factor, which we're gonna show later, times the straining action or internal forces due to this type of loading. So for example, if you have a dead load can cause axial loading, shear, and moment. And if you have live load, you have similar axial shear and moment. You have to multiply that time the loading or the internal action to pump them up. However, in your resistance side, which is depend on your cross section and material properties, etc., you will use a reduction factor for strength, and it's also per internal force. For example, the moment capacity can be reduced by a factor, shear, etc. So you will increase, you reduce a little bit your resistance, but same time you're gonna be increasing the load by factor, the difference between the demand and resistance has to be lower than 0. So if we show what are a contributing factor for both load, demand and resistance, you have a bridge, let's say half two span bridge that can be modeled in two span configuration. You first of all, you need to develop your bridge model using hand calculation or finite element models. You need to do structural analysis. Let's say you have dead loading. We will see dead load divided by DC and DW later on, and you may have some moving loads, right, that moves across the bridge. So you need to come up with your structural analysis under the applied load, is it dead load or live load, to get your ultimate axial loading, ultimate shear loading, and ultimate moment loading. And you have to do it for each type of loading that you are expecting on this bridge and combine them with different loading factors to get your demand side, which is summation of load factors time your loading time. In the resistance side, you may have a steel girder or concrete girder, correct? And you have to define the cross section. This case, maybe this is steel girder. You need to define the materials. So material that include material, reinforced concrete, structure, steel, etc. Your shape, in this case, I shape or W shape or rectangular. And you also need to calculate the response of this cross section to the axial load, shear, and bending in terms of capacity. Like what is the moment plastic moment capacity of the steel girder, or the moment strength of pre-stressed girder, etc. And as we discussed, the right side resistance Rn has to be bigger than the left side or equal the demand, right? So let's go back and focus on what type of loading that we will be dealing with in bridge design. So we have several type of loadings. The first loading are permanent load. We can group the loading to the permanent load, which you always experience on bridges, or transient load. Transient loads are not permanent through the bridge. So in terms of dead load, we have two components of dead load. You will have DC, which is dead load of components, which for description, we can say dead load of structural component and non-structural attachment. Mean that if you have bridge deck, the weight of the bridge deck is a weight of structural component. The own weight of the girder are DC because of the weight of structural component. DW is the weight or dead load of wearing surface, which may be or utilities, which may be a future overlay or future utility addition. So this is DC and DW. So your dead load is either dead load or weight of the components or weight of future wearing systems, wearing or overlays, as they call it sometimes, overlays or wearing surfaces. For your transient loading, you have different type of loading. You have live load, which is related to pretty much live load of trucks. You have IM, which is vehicular dynamic load allowance. Your trucks are not moving in very slow speed that can be considered static. It moves in a certain speed, minimum to maximum speed allowance, so allowed by officials. So you will have impact on your different impact effect for different component in your bridge. That's why you have what's called dynamics load allowance IM from impact. that has to be added to amplify the constant weight of the truck. We have also uniform temperatures. Remember, our bridge are exposed to environment. We are here in cold region. Sometimes in some region you can have variation on temperature. Some regions like Texas and Arizona and Nevada, you will have high temperature up to 120 Fahrenheit, which can lead to expansion of materials and can impose loading to the structures if some movement are restrained. So those kind of uniform temperature that can cause some internal forces in your structure. You also have gradient temperature, GU, which if you have, for example, this is your bridge superstructure and this is your bridge substructure. Usually your top of the girder is exposed to the sun while the bottom of the girder is kind of shielded from the sun. So you will have higher temperature, let's say 120 feet Fahrenheit in this side, but maybe 90 feet Fahrenheit from the other side. And this will cause internal force, not only axial loading, but also moment due to the gradient in temperature. You also have earthquakes, that's extreme event, and we have also wind loading either on your structure. Imagine if you have 7-8 feet deep steel built up section and this is exposed to wind loading, that will be lateral forces on your bridge superstructure and substructure. Also trucks that moves over bridge. Let me say this is your truck and maybe this is your truck height. The wind also affecting the side of the truck, which has to be transferred down to the bridge deck by friction between the tires and bridge deck. So this is also called wind loading on loads, on live loads. So all those loads, as we're going to show later on, are transient and natural. They are not permanent on the structure. Here, pardon me, and my video is shown in the slide covering some of the graphs, but here we are showing again what difference between permanent load and transient loads. So permanent load, dead load, for example, you will have constant amplitude over time. You may have sustained live loads of car convoy of trucks that move over the bridge all the time. But for the big trucks or design trucks, you may have it as transit over time. So are not constant. You don't have a design truck moving all the time. Your temperature, if you have winter season, you may have snow, and you have summer without snow. Earthquake takes years to happen, and wind are also based on the design amplitude in terms of like the speed of the wind. It's not always high speed, so they are vary over time. This schedule is very nice to show what's the difference between permanent loaded and transit loading in general, but also the peak and frequency of each of those loads. We can go back now and touch base on design philosophies. The first design philosophies, which is from 1900 to 1960, was predominant in WSD or ASD, working or service loading. So in this philosophy, we are, for example, if you have a structural element, we will use a safety factor or safety factor omega. So you will actually divide your capacity by a factor. Let's say you have steel concrete and you get compressive strength of 5 ksi, you will divide the 5,000 psi that we mentioned over safety factor. And when we use this one for your design, you will not increase your load, but you will basically reduce your capacity or compressive strength or steel yielding by safety factor. This actually method is used when you have uncertainty, high uncertainty, similar to the geotechnical engineering. Right now, they still use those methods. They are not allowing much deformation in a design level, so you are not allowed to get much cracks in your concrete. So they are used also in designing fluid filled structure like water tanks. We are using it for calculation of deflection, cracks, and stresses in pre-stressed concrete. Uh, the method use a factor of safety or safety factor for all loads, does not count for variation in resistance. So I mean that you may have one design based on 5,000 psi concrete compressive strength. However, because you intend to design for this value, you divide over the safety factor and you go away from any variation that could happen in the actual construction. In your LRFD, which started this approach in 1963, is more rational than working loads, provide more realistic assumption on safety, and produce economical design. I mean that we need to consider variation. We always go in estimating the capacities or capacity of different systems or elements such as concrete girders and steel girders. We know pretty much the cross sections. We know pretty much what type of materials. We have a control on testing materials. So we don't need to reduce it by that much. We reduce it by a little bit, which is a reduction factor in strength. However, this also method account for variation on those calculations. Let's say you design for 5,000 KSI, but you take samples from the site and there is a variation between the cylinder's compressive strength must also be counted on in a probabilistic framework. It's more rational than working load because provide estimate and produce economical designs. Loads are multiplied by load factors. So as we mentioned, the loads are amplified by factor because we may not have better control on how the structure will experience the loads. Because you may design and intend to design a structure for a certain live load, but in increase in live load could happen like over size trucks or uh, a big loading on buildings. So you amplify that to account for uncertainty in loading, but since you have better control material, you don't reduce that much, similar to that working load design. Nominal design are multiplied by the strength reduction factor phi, as you can see here. So we reduce it, but we don't reduce it by safety factor. We reduce by strength reduction, and based on how we are in desire of certain type of failure. Like for example, ductile failure of concrete beams is desirable. So when you reduce moment or flexure strength, you decrease it by factor of safety between 0.9 to 1 actually. If you're failing in shear, your reduction can be 0.75, etc. So going back to the probabilistic based specification, so your load and resistance can be represented as random functions. So this is a distribution function for two type of distribution. Let's say this one, you have a distribution function where you have your mean value and the small standard deviation. because this can present resistance very well, because we have better control on cross section, we have better control on the material, but we don't have better control in loading. So a large standard deviation can happen in this case, and this will lead to uh, uh, implication that this is a less predictable cases for loading, not similar to your strength or resistance. So left side will show the demand, right? So very much you will have your mean value of loading, and you will have your nominal value of loading, which what you desire, and you have gamma times the mean value, or sorry, gamma times the desired value. So you desire for this loading to happen, and you magnify it by a factor gamma, and you also, it may happen in a mean in a distribution different than what you expected. It may actually be perfectly on top of each other. For resistance, let's say also the same condition. This is you have so many concrete cylinders. Let's say this is a very simple example, and you design for 5 KSI concrete, right? So this 5 KSI is this value, which is a nominal concrete strength. It came to the field, different trucks, different samples. The mean of the values came a little bit higher. You need to differentiate between the two, the ratio between the two called bias, and you use the nominal strength, you reduce by a factor phi, you go to the line that is called phi Rn. You know, phi Rn has to be bigger than gamma or equal gamma qi, right? Summation of gamma qi. So here is the same case. You may design for a load of 2 kips per foot. The loads condition could be a little bit different when you have the mean over the time of the structure, loading time of the structure, which is QM. You also use your nominal loading multiplied by gamma factor, increase it for if you remember from steel design or concrete design, we multiplied dead load time 1.2 and live load 1.6. So in this curve, you always try to, if you draw them side by side, the resistance factor has to be always on the right side of the loading factor of the demand, and they may intersect. Once they intersect, this means that your design is less is not safe in this case, because loading is higher than the resistance. You can take the different function between R bar and Q bar, and you will develop your own distribution function. And this part of the distribution function where the failure happened and probability of failure. For example, in this part of the equation or the curve, the loading Q will be higher than R. However, from this vertical axis, you have a safe design. You also have the mean of R minus Q bar, R bar minus Q bar, and the mean to the vertical axis can have a value called beta time standard deviation, and from this distribution you can get the standard deviation. So the beta is the multiplications of standard deviation, and we are always in desire of having 3 to 4 in LRFD, which correspond to 10 to the power negative 3 to 10 to the power negative 4 probability of failure. And you can see here this equation, I hide it but with a video, but you can see here this side is sigma square q plus sigma square q, and based on your beta value, you can go for this um, table and find your probability of failure. Okay, so just go back to some statistics that you need to review if you have a distribution. This is for um, dice, two dice thrown same time, and you add the value on the top faces. So for example, you have 1/36 probability of having the two numbers added to each other to be 2, which is 1 and 1. You have two chances, or 2/36 chances to have the addition to be 3, because it could be 2 and 1 in one, 2 and 1 die, the dice and one other dice, or vice versa. Addition to be 4 can be done by 1 and 3, 3 and 1, 2 and 2. Addition of 5, etc. Addition of 7 can be done with 6 and 1, 1 and 6, 5 and 2, 2 and 5, 3 and 4, and 4 and 3. So those give you 6/36 cases of this addition. You have one chance of having 12 because it's only happened one time, 6 and 6. If you use this, if you have this distribution, you can actually get the mean value, which is the value times the frequency. The value times the frequency. So for example, the value is 2 and probability of happening is 1/36, and you divide and you keep adding them and divide by the summation of probabilities. And you can have the variance from this equation, which depend on also the mean. Standard deviation is a positive square root of the variance, and you can have this normal distribution constructed for you using this equation. If you go back to LRFD and ASD and you calculate your beta value, if you remember your beta, which beta was when you have your distribution between R resistance bar, R bar minus Q bar, and you have this as where you will have the load more than the resistance, and the distance between the mean to the vertical axis where the value R bar minus Q bar would be 0. You have beta times standard deviation, and you have a better control in LRFD to get your beta values based on the loading factor and the resistance factor. This example was for a steel girder, where we have different spans, and you always will see that your reliability index is more between 3.5 and 4-ish, while because you have a wide range of safety factor that you can take when you design your girder for ASD, it actually varies quite a bit for different spans. So LRFD give us more probabilistic framework to design our bridges, and your reliability will be really close. This is we are now moving to section number 1 from AASHTO, which is introduction. In section number 1, we are showing the main equation that we always thought of. QRN is the resistance side, and somehow called RRR. And we also have gamma Q, which we discussed in few slides before, but now we have eta factor, eta I, and it's addition to this equation. And eta I is factor that rely on 3 major factors. So the eta I is multiplication of eta D, eta R, eta I, D for utility, R for redundancy, I for importance, as we're gonna see here. You have phi is a resistance factor that reduce your resistance a little bit. Rn is a nominal resistance, Rr is a factor resistance, and you also have Qi, which is a force effect or demand, and you have gamma I is a load factor. So let's go one by one, eta D, eta R, eta I. So in eta D, which is ductility is in our design, we always like for ductility during failure. So you produce more cracks and sign of failure to warn um, drivers or traveling public or occupants of structures by failure. So the system of the bridge shall be proportional and detailed to ensure development of significant and visual inelastic deformation in form of crack here at the strength and extreme level before failure. So this is a good sign of your design. You don't need your structure to be brittle failure, it fails right away. So if your structure is designed with non-ductile components, let's say, you will have your gamma D more than 1.05, so it's increased by 5%. If you are using conventional design and detailing that comply with specification, you don't worry about this factor, it's always 1. If you add more component that enhance ductility component connection that maybe have more ductility enhancement measures beyond the requirement of this code, you may reduce your load by 5%. This is all for strength limit state, which we will discuss later. For all other limit states, just 1. For redundancy is your structure has only one load path. If this load path erupt by any failure, mean that entire structure will fail. If you have more redundancy in your system, it's always positive. So the definition of redundancy is multiple load paths that and continuous structure should be used unless they are compelling reason not to be used. So if you don't have any redundancy, which is sometimes called structure critical or redundant member, you have to increase your load by 5%. If you are using this specification and you have conventional level of redundancy, where phi already account for redundancy, so it is can be just 1. If you have exceptional level of redundancy beyond continuity, like so you have extra girder in your design that if it's one girder failed, other will carry the load, etc. You are allowed to have 5% reduction. This all happen in a strength limit state. For all other limit states, you just use 1. For operation, is this really by owner, because the owner may declare a bridge or structure component to be of a priority in terms of operation. So if you have critical or essential bridges, you may have 5% extra when you are designing in terms of loading. If you have typical bridge, you always use 1%, 100% or no increase or no reduction. And if it's a less important bridge, you are allowed to reduce it by 5%. This is all for strength limit and not for others. Other always I is 1. Make sure that when you add them multiply them up, you also don't go more than 1.05 or less than 1.95. Let's now cover the limit states, which as we mentioned throughout the last 24 slides. We do have what's so-called recurrence of events. So let's say we mentioned the live loads, temperature, wind, earthquake. We need to find a way to define limit state, which is also will result in load combination that we will design for. A normal recurrence mean that it is service limit state. So this is a usual daily operation and service of a bridge. You don't have the extreme event or strength limit state every day. So normal recurrence will be service limit state. Frequent recurrence will be strength limit state or fatigue and fracture limit state. And rare recurrence, which means like you have extreme event, if you have an earthquake or collision or something. So you will have constructability limit state, which is a limit state during construction. You will have a strength limit state, which is to ensure strength of and stability. Both local and global are provided to resist specific load combination that bridge expected during the life. So we'll say in this case, we will use a higher load factors because we will say we can estimate this load to be in this level, but maybe live load could happen and happen overloads. So we will make sure that is still structure has enough strength and stability for this limit state. For surface limit state, ensure restriction on a stress deformation crack under regular surface. So you don't need to exceed certain cracking limit or deflection limit during the daily operation. You have fatigue and fracture, which is material specific, especially for steel. You have extreme event, which is also to ensure life safety of traveling public. Here, we discussed earlier the type of load from permanent loads to transient loads. So for this case, we will go one by one to discuss every dead load time and live load, etc. For a permanent load, DC and DW, dead load shall include the weight of all components of structure, appurtenance, and utility attached thereto, each earth cover, wearing surfaces, future overlays, and planned widening. This is from the code. And in this table, you will see the unit weights of different materials. You can see here, I'm covering it a little bit. Steel is 0.49 cubic feet. Concrete, they range from 150 pound per cubic feet to a little bit higher due to the compressive strength that you can be obtained. So reinforced concrete is 150 pound per cubic feet. Steel is 490. You will get your cross section. You multiply times the area. Unit weight time area. You get your load distributed kip per foot. General ranges for box girder and steel girders, it's 10 to 15 kip per foot, or 4 to 6 kip per foot for steel brake girder. This is the table that you need to go, table 3.5.1-1. For different material, you can get your own weight. So it's on chapter 3. DW is related to what's we call count for asphalt concrete overlay after 15 to 20 years. So every 15 to 20 years, we have to rehabilitate our pitch decks and add future wearing surface in terms of asphalt or concrete overlay. Oftentimes they are 3-inch depth, and the weight of bituminous wearing surfaces unit weight is 140. And if you take a 3-inch thickness of asphalt concrete, it is always going to give you 35 pound per feet square. So this is actually summing the dead loads. So now let's go for more descriptions about live loads. So in this example, we will cover live loads pretty much in your first assignment. Problem number 2, I asked you to lay out in the cross section the spacing between the girder and overhang based on simply supported or continuous spans for steel girder or box girder. So we're going to use it very much here. You are now familiar on how to general rule to lay out spacing. So in this example, you have four spacing of 9 feet, 9-inch. Total center of exterior to center of exterior girder is 39 feet. You have two overhang around 4 feet with 3 feet 11 and quarter inches each side. And this will give you the full width of 46 10 and a half, 46 feet 10 and a half. So we are very familiar now on how to lay out those distance. However, uh, the drive or the width of drive is different because you will have a barrier to ensure safety. So you will have a width of barrier where the loading can start for the live load. Here we are talking about design trucks. So let's say you have to put the barrier from this side, barrier from this side. The width of the barrier is 1 foot 5 and a quarter inches. So you have to subtract it from 46 10 and a half inches. That gives you clear 44 feet for this example, a width of a roadway where a truck can be anywhere through the width. We know that you have to have a marked lane on your roadway and bridges, but we usually don't count for that because drivers can really violate those lines. So we need to find a way how we gonna find the loads, okay, for the live loads. For live loads, which we donate to by LL, the design lane width is 12 feet. So if starting from the edge of the barrier or the rail, you have to find what's so called your design lane, and its width should be 12 feet. In this design lane, the 12 feet, your truck can be anywhere within the 12 feet. And you can have as much possible of design lanes. For example, in this case, you have 44, right? So you can have one, which is 12, another one give you 24, another one give you 36. However, if you add another one, it is 48. So you cannot have actually a full design lane. So you only, in this case, you have 3 design lanes, okay, which each can be should be 12. Those design lanes are not fixed, as you can see here. They are also moving laterally, so they can start from this edge to end in this edge. But in terms of how to calculate those design lanes, you take this number, which is what's called edge of barrier to edge of barrier distance, and you divide over 12 and you get the integer number. Okay, so number of design lane is bridge width, barrier to barrier, rail to rail, divided by design lane. Okay, in general, bridge width minimum should contain 2 lanes, so it should be at least 24 feet. In some cases, it can be 10 because within this 12 feet design lane, your truck design truck is 10 feet width, so it can be within that 10 feet. In this case will make you having 2 lanes of 10 feet restricted, so 20 feet restricted. By minimum should be always preferable to 24 to design lane. We have what's called multiple presence factor M. In this case, let's say I will design a bridge where in one case I know that I have maximum of 3 design lanes, okay? But in some case, you may not have the design truck in all the 3 lanes in the same position, in the longitudinal position. So you may have different type of trucks, but the design trucks truck is only occupying one lane and not in the other lanes. You may have side by side two design trucks in the same longitudinal location, same time. You may have now three design trucks in the same longitudinal location, same time. So it's probability. So if you have only one truck, we increase the load by 1.2 factor to say, okay, it's really underestimated to have only one truck in the same position, longitudinal position. You may have only factor of one. If you have two design lane, will mean that you will have two trucks in the same longitudinal direction, same time. But it's really hard if you can have three or four design trucks, same location, longitudinal location, side by side. So this factor is called multiple present factor, presence of lanes same time simultaneously. So you need to use this factor to either amplify or reduce your loads. Your loading, the important one was called design truck, which is HL93. It's combination of two. It has design truck or what's called design tandem, and it's combined with lane load of 0.64 kb per foot. Let's discuss every term here in detail. What is design truck HS20-44? So this is your design truck. Your design truck is a semi-trailer, which called HS20 S16-44. For abbreviation, we called HS20. 20 is related to tons, so it's HS ton. So your trailer, semi-trailer, is this part of the truck. This is a trailer. It's actually 20 ton or 44 or 40 kips, sorry, 20 ton or 40 kips, and established 1944. So in this truck, you will have 8 kips in the front axle, 8 kips or 4 ton. In the rear axle, you have 60 ton or 34 kips. They are spaced at 14 feet long. This is longitudinal direction, right? So the trailer is two axles. We call this axle. Okay. The summation of the load on each tire wheel is 8 kips for the front, 32 for the rear. You can see in the bottom plan, you may have, this is your axle, front axle, this is the rear axle. Okay, and the distribution of 8 kips will be like 4 kips here and 4 kips there, and 32 will be 16 kip and 16 kip. It's also combined with semi-trailer, so it's truck with semi-trailer. Here is the front, and this is a semi-trailer, and the axle is also 16 tons, similar to this rear, for 32 kips. So you have 16 in this one and 16 in that one, right? The spacing, it actually gives a variation of spacing between the rear axle and the trailer axis to be between 14 to 30 feet. So you are actually have exchangeable distance here based on your semi-trailer. Okay, the distance between the wheels, W's, are 6 feet, and the total depth is 10. And this is what we're gonna discuss in the next slide. So you always have the truck front axle, this is called axle, 8 kips, rear axle, 32 kips. The distance between them, 16. You have two lines here, wheel lines. So you can divide 8 to 4 and 4 kips, 32 to 16 kips. This can attach to semi-trailer of 32 kip at the distance varies from 40 to 30 feet. In the next slide, I'm showing the side view. Here is your wheel axis or distance between the wheel, the 6 feet, and the total width of your truck is 10 feet. And remember, this here start at, this is a curb, so they start at here. So if you have a barrier system, say this is your barrier and this is your overhang, you start from here, putting at 2 feet your first wheel axle, 2 feet. You put your first load in the transfer direction, and at 6 feet, you put your second one, and you end up with the end of your truck. Remember, the truck is 10, but the design lane is 12. So we will show how we have to lay out the trucks later on. So the second part, called design tandem, is very similar to trucks, but it's only 2 axle, 40 kips total. The axle weight each 25, so each wheel is 20, 12 and a half kip, adding to 25 here and 25 there. The distance between them is 6 feet in transfer direction, similar to a truck, 6 and 2 each side. Distance between wheel, but difference between axle is very close here to only 4 feet instead of at least minimum of 13 for the design truck. They has to be combined with uniform load of 64 pound per linear foot loaded lane, and this represents convoy of trucks before, ahead of the truck, and behind the truck, and under the truck too. So you have to, if you are loading your longitudinal girders, okay, let's say this is your bridge, you have to add live load of 0.64 kip per foot uniform load. It acts on a width of only 10 feet, so it's attached to the truck width. And let's say your truck will be, this is a front axle, this is the rear axle, and it's a trailer axle, and you have 8 kip, you have 32 kip, and another 32. And in during the analysis, we will show how those loads distribute to the girder that carry the superstructure. You also have different trucks called permit trucks, which is per the state regulations, state by state. So in addition to HL 93, in a state limit 2, we can display that or explain that later on. You have permit vehicle load configuration. This is a vehicle configuration from New Jersey. You'll have front wheel of 16 kip and distance of 12, and 3 axle loads of 16, 28, 28, space at 4 feet, another distance of 21, and 28 kip 4 of axle spaced at 4 feet. If you go for New Mexico, this is how the truck will go. For example, you carry the beam, you may have 27, 25, 25, 25, series of 25s. This called B13 because it has 13 axial loads. You can count 1, 2, 3, 4, or axles, 5, 6, 7, 8, 9, 10, 11, 12, 13. And the spacing are also here around 18 feet spacing, and this is a plan view showing the loads. For example, the 27 here, 13 and a half and 13 and a half, and every other wheel you have 4-wheel axes, and each wheel will give you 6.5 kips, adding to 25 kips each. Here is a California truck, as you have so many different, so P5, 7, 9, 11, and 13. For 5, you only have 1, 2, 3. This is your truck, and you have trailer. Another one, you have to have 2 axles, right, to make either 5, or another 2, 7, another 2, 9, another 2, 11, and another 2, 13. We need to count for the dynamic load allowance. What we discussed earlier is your truck is not moving in extremely slow speed to be considered static loading. It moves with speed and has dynamic effect on the substructure and superstructures. So you have a series of spring and damping systems in any truck. And there is huge research done to get those numbers in how to amplify your weight, which can be considered static, by a factor to consider dynamics. So for example, here we are showing the span deflections based on numerical models and some experiment. We have the static line for deflections and dotted line, while for dynamic line is continuous and solid. And you can see here there is the amplification between the peaks, and this has to be added to your design to count for dynamic load allowance. And as they are based on the elemental components, for example, if you have bridge joints, the tire is very close, it has adverse effect on those joints, so you amplify by 75%, while for this other substructure, fatigue, fracture, limit state, you use 15%, and other limit state use 33% amplification. Here is another amplification that in terms of stresses, so you can also see it in the stresses and loading, that you have to amplify by factor IM, which is a table 3.6.2.1-1, counted for truck loading, count for design tandem, which everything has axle, but for uniform load, which is 640 pound per foot, don't count IM or a dynamic load allowance. We also have other loading, earthquake. This has to be a separate course. Wind loading from wind on superstructure in live load wind on structure. You have temperature, can be uniform or can be gradient. Okay, we will cover only in this course some of the loads, which not all of the load. We will, for example, focus on uniform temperature TU. For uniform temperature, the temperature variation caused by superimposed deformation in the bridge. So as I described earlier, you have a big steel girder of a, let's say, 150 feet span. If you have high temperatures, they are expanding. If you are allowing the deformation, nothing will happen. If you are locking the deformation, so you not allow lateral deformation, they impose axial loading on your structure. So a lot of these section 3.1, longitudinal loading due to expansion and contraction of statically. So even in low temperature, when you have, if they contract, Also, if you restrain the movement, it may add to the loads. You may have also some rotational loading due to temperature gradient we will not cover in this class. So let's say equation here. Let's say you have a bridge with the sliders on left side and right side. Your center of movement will be the middle of your girder if it's a symmetric girder. So basically, if you mean center of movement, you have a distance L, which can be expanded due to temperature left and right. So this is going to be your length of temperature expansion or contraction. Let's say your system now is in a roller and hinge, mean that you are not allowed, pardon me, this should not be here. You are not allowed to expand in this line. So it's fixed, and all the expansion has to happen in this line. So this is your distance L, okay? Because you are locking the deformation here, not allowed to move it, but everything will move this direction. So what you need to do, if you have a structure with multiple rollers, so you are allowing all the deformation to happen, you want to see where is your center of mass, and from there you measure your length of deformation that allowed, right? If you are locking one of, like this is ruler, this is not allowed to move, and this is ruler, and this is ruler. Now your fixed point is around the fixation of the hinge. So you'll have L1, L2, which will be this distance L2 and this distance L1, right? So L is the length subject to a temperature change. Delta T is temperature change, and gamma alpha is coefficient of thermal expansion is 6.5 10 to the power negative 6 10 to the power negative 6 for steel and concrete respectively. So you can use this equation, the deformation delta L equal gamma L delta T. So for example, in this case, if your span is 400 feet, so your L length of deformation is actually 100 feet. So what you need to do, if the temperature change from, let's say, 30 Fahrenheit to 100 Fahrenheit, your rate of change from 30 Fahrenheit to 100 Fahrenheit is a difference between the two. So your delta L change will be gamma. If it's a steel, you will 6.5 times 10 to the negative 6 times the change in temperature here will be 70 Fahrenheit, 100 to 30 times the length 100 feet. You can multiply it times 12 to get it in inches. So you can expect some problem like that in homework and assignment quizzes, etc. And here we are showing in some climates a typical change in concrete and steel. This was from earlier version of code, so 70 feet and 80 feet for cold and moderate weather, and you can say you have if you have freezing days less than 14 days, you are considered moderate climate. If you are cold climate, you have more than that. So in steel, the variation in moderate will be 120 feet, sorry, Fahrenheit change in temperature, and 150 for cold. The limit state back to the constructability limit state, strength limit state, service limit states, fatigue fracture limit state, and extreme events. Limit state and load factors and load combination are really one subject that should be taught in one subject. So load combination. You have a rule called Trextera rule of load combination, we mean that not all the bad thing will happen at the same time. So it says do not all bad things do not happen at the same time. So based on the observation that one load combination reach at extreme event, other loads don't acting at the average value. Meaning that if you have earthquakes, wind will not happen. If you have extreme collision, maybe also earthquake will not happen. Murphy rules, everything will, if something gonna go back wrong, everything will go wrong, right? So usually the code used Siska rule, which extreme events are independent from each other in terms of the maximum loading. So if you go to the table 341-1, you have the load combination and load factors. Okay, you have the strength load combinations or limit state. You have two extremes. You have 5 off strength, I, double I, triple I, IV and V. Extreme 1, extreme 2. You have 4 off service, 1, 2, 3, and 4. And you have 2 fatigue, fatigue 1 and fatigue 2. You have all the loads here, like DC1, DW, DD, EH, if you will know all of terminology. Live load, IM is impact factor or dynamic load allowance, etc. So those are type of loads. And here where you can find your load combination. It's a little bit tricky, not straightforward as building your dead load is 1.2, live load 1.6. Here live loads in strength 1 is 1.75 and strength 2 1.35. We will go load by load, defining load by load and defining most of the load combination here. So let's say you have permanent, what is your permanent load? You have CR is force due to creep. You have DD, which is down drag forces from waves. You have DC, which is dead load component of weight of components. DW is dead load of wearing surface. You have EH, horizontal earth pressure. EL is essential locked in forces effect from construction procedure. So let's say you have a construction that locks some stress in your structure and you carry over to the surface level structure. You have ES, is earthquake subcharge loading. You have EV, which is vertical pressure from dead load on earth fill. You have PS, which is secondary load post tensioning, and you have effective shrinkage SH. In our class, we may focus only on DC and DW, and we will let you know once you know if we can't touch others. If you can see here, the load factor are all gamma P, so they are not very specified. You have another table to specify the P, so we will go through that. Other transit loads, you have blast loading, BL, you have vehicle braking force, PR, you have centrifugal force, CE, you have vehicle collision, CT, you have vessel collision, CV, you have earthquake, EQ, you have friction load, FR, ice load, IC, IM, vehicular dynamic load allowance, LL is live load from vehicular, LS live load subcharge on a soil, when the live load moves on the soil. You have pedestrian live load, PL, you have force effect on settlement, SE, you have force, this is what we discussed, is temperature gradient, temperature and uniform. We have water load, stream pressure, wind on live, and wind on structure. So this actually to give you a sense how what are those like abbreviations for the loads. Okay, we need to also consider that what are those limit states and how to get those factors. So if you go to section 3 in AASHTO, I'm putting here all the section numbers. If you want to go for dead load DCDWEV, you are going to section 3.5.1. earth loads, EHESDD, section 3.5.2. For live loads, you have section 3.6 describing 8 different type of live loads. Sorry, 5 different types of live loads, from gravity loads, LLBL, dynamic load allowance, centrifugal force, Pagan force, and vehicle collision forces. You have 3.7 water loads. Wind loads are 3.8, include load on wind load on structure, on live load. You have ice load, section 3.9. You have earthquake load, section 3.10. You have earth pressures are 311. And here you can 3, 5, 6, and 8 will give you all down drag, ES, ELS, and EH. Force effect due to superimposed deformation, uniform temperatures, gradient temperature, section 312, 312, 2 and 3, and even differential shrinkage, creep, settlement, pre-stressing, stress imposed structure, friction, and vehicle collision. So those are where you can go actually to your AASHTO specification section 3 and find more information about those loads. We covered here 3 different types of loads: temperature loading, live load, and dead load as a starting point. So we need to know the factors. The gamma factor that we showed up earlier, it has minimum and maximum. So let's say you are dealing with DC component and attachment weights. If you are counting for all cases, you will have a minimum value of 1.25 and maximum value 1.25 and minimum of 0.9. So basically, the first decision, you go for maximum. Your dead load is 1.25. Your live load is 1.75, for example. In this case, for dead load, you have minimum and maximum range from 0.9. If reducing the load will impose much critical situation to a bridge, and 1.25 is increasing the load will impose more critical situation. So what is maximum? What is minimum? Maximum if the dead load internal forces have same sign as live load forces. So your live load and dead load are the same sign. So when you're adding the two factor, you have to use the maximum factor for dead load and the factor for live load. If the maximum and dead load and live load are in different sign, you need to use a lower factor for dead load, which is in this case 0.9, to increase the internal forces in your structure. So here are where you can get all your gamma p value from the first table. So let's go case by case. First case called strength 1. Okay, strength 1 is basic load combination related to normal vehicular use of bridge without wind. So it's very clear. It says usual operation. So you have the dead load, you have the live load, but you don't have wind because it's called without wind. So in this case, as you can see, you may have a dead load, right, DC and DW, and you have to get DC and DW from gamma P from the table that I just showed on the previous slide, and your load factor is 1.75, and you remember live load and IM are kinda concurrent, so in this case your load combination will be gamma P times DC plus gamma B DW plus 1.75 live load plus Y plus IM. You may have friction force and others that you can consider, but in this class we will not focus on that. So this is the easy way to show. The second load combination is strength 2. So read the load combination. It says relating to the use of bridge owner special design vehicle, which is permit truck. So when you use permit truck, use your load combination 2, but your input truck, permit truck or special truck in strength 2. It's also without wind. So all the difference between this equation and this equation is the factors drop from 1.75 to 1.35. Okay. The next strength 3, is a load combination related to the bridge exposed to design wind speed at location of the bridge. So it doesn't actually include live load. It includes the dead loads, gamma PDC, gamma BDW, and include one WS or WA or WL. It doesn't include WL, it has WS, which is wind on structure. Okay. Strength 4 is load combination emphasizing dead load forces effect on superstructure. So this is for bridges that have high dead load factors. So it's always going to be 1.5 DC in gamma BDW. If you go to the table for gamma B in this case, it will show you for strength 4. It's 1.5, not 1.5. It's when you have a bridge that has significant ratio between dead load and live load. So the ratio is very high, dead load compared to the live load. Load 4, which is basically much related to normal operation of vehicle load, but wind speed up to 80 miles per hour. You will have gamma B and gamma B for DC and DW. You have 1.3. Here we have an addition of live load. So 1.3 live load, and you have one of wind on superstructure or on the structure and wind on live load. So this is all the 5 strength limit states. If you go for extreme event 1 is load combination including earthquake. The load factor for live load is gamma E quake, and gamma E quake and determine project-based specification. So it's actually how much percentage of live load is allowed when you do the earthquake calculation. So it's always one for dead load, one for design. So live load is not included here because does not combine with IML and IM plus N, because we are using Kruszyska rule, which means that earthquake will not happen during the extreme live load or normal live load operation. So you only have one factor for DC, one for DW. You will have one for earthquake. Okay, which pretty much you can see it here. Okay, this is extreme 1. Extreme 2 is for all other extreme event load combination related to ice, collision, vehicles, flooding, hydraulics events, hydraulic event, etc. And they don't have happen concurrently. Okay. Service 1 is load combination related to normal operation use of the bridge for a speed of 70 miles per hour for all loads taken to the nominal values. So this we are used for deflection control, buried metal structures, concrete cracks on reinforced only check concrete cracks, transfer analysis related to tension in concrete segmental bridges. So it's in very specific cases you use those factors. It's always going to be normalized at 1. Service 2 is load combination intended to control yielding of steel structure and slip critical connection due to vehicle live load. So this is more like steel structures, and access to road bridge truck loading conditions such as access road to port and industrial sites. So when you have it's a specific case, you check for service 2. Service 3 is more like a pre-stressed load combination analysis related to tension in pre-stressed concrete superstructure with objective to control the cracks and principal tensile in the webs and segmental bridge concrete. So you usually have service 1 for steel and service 2 for pre-stressed, service 4 of only tension pre-stressed column when subject to crack control, Fatigue is, we're gonna mention that a lot in the steel design or steel structure sections. Topic number 6, fatigue load combination related to infinite load induced life. So fatigue steel structure actually has fatigue issues, which we how many cycle of loads that you have over time. So if you design for infinite loads, you use fatigue number 1. If you limit your number of uh, truck movement over the bridge to per the life of structure, you have finite load induced fatigue, use factor load combination fatigue 2. And by this actually this conclude the topic number 3 for loading. Don't forget that we still have an additional um, session with Mike Coleman on February 13, 6:30 p.m. This presentation was recorded off the class to provide additional information, and student can go back and check the video later on uh, for better understanding of the topic, but may not include the exact information in the class. It's just for reference. The interaction between me and the student during the class will be in terms of questions, maybe ongoing, assignment, etc., or quizzes is not included in this record. Just to give a reference for a student as time flies during the semester, to go back and watch part of this presentation to remember some explanations. So thank you very much for staying tuned.